Okay, so in this problem, we have 6 oranges and they weigh 2 pounds 4 and 13 ounces. And then we cut them open, squeeze all of the juice out into a big measuring cup, and then we weigh what's left after we take the juice out. So that'll be the pulp, and the orange peels. And we figure out that that weighs 1 pound 4 and 12 ounces. So therefore we know how much juice we got out in terms of weight. And then the total volume of the juice that we squeezed out is 1.75 cups. And the goal of this is to get the specific gravity of the orange juice. And they want us to state any assumptions that we make. So, ultimate goal, specific gravity of the orange juice. All right, so we know that specific gravity is equal to density of the juice over a reference density. And that reference density is the density of water. And so to get the specific gravity of the juice, we know the density of water, we need the density of the juice, which is equal to the mass of the juice over the volume of the juice. So to get that, we go back to the information that we were given. So we know that the mass of the oranges is equal to 2 pounds 4 and 13 ounces. And that is going to be equal to 2.8125 pound force. And then we squeeze all the juice out, and then we weighed the pulp and the orange peels, and we figured out that that weighs 1 pound 4 and 12 ounces. So M, pulp and peels, is equal to 1 pound 4 and 12 ounces, which is equal to 1.75 pounds. And since mass of the oranges is the total mass, and we know what we have left after we get the juice out, then the mass of the juice is just going to be mass of the oranges minus the mass of the pulp and peeling, which is going to be 2.8125 pound force minus 1.75 pound force. And what we're going to want to do now is convert this to pound mass, because we want this in mass units. So convert from pound force to pound mass. So 1.0625 pound force. Oh, sorry, I didn't put that up here. This is equal to 1.0625 pound force. So we're going to multiply this by 32.174, 32 pound mass feet per second squared over 1 pound force and 32.174 feet per second squared to get 1.0625 pound mass. And then from there, we know that we want our density to be in units of mass over volume, and we're going to assume that our reference density of water is in grams per cubic centimeters. And so density of water, grams per cubic centimeter. So then we want to convert pound mass to grams now. And that conversion is going to go like this, 1.0625 pound mass. And let's take out this conversion table again. So we are going to have 1 pound mass per 453.593 grams. And that is going to give us 481.9 grams. And that is our mass of juice that we need up here. So now we have our mass of juice, we need our volume of juice, and we already have that. That's 1.75 cups, but we need to put that in the right units. So now we need to get our V juice in the correct units. So we are going to convert volume to centimeters cubed to match the units for our reference density of water. So this actually isn't in the conversion table, but this is kind of a conversion you can find on Google for cups. We don't really use cups too much in chemical engineering. Actually, I don't think we use that at all. But this is oranges, so it's a little different. So V of the juice is equal to 1.75 cups. And the conversion for cups to cubic centimeters is going to be 236.588 cubic centimeters in 1 cup. And that is going to give us that we have 414.029 centimeters cubed. And that is our V juice that we're going to plug in up here. So now we can get our density of the juice. So that is step 4. Get rho juice. So rho juice again is equal to mass of the juice over volume of the juice. And that is going to be 41.9 grams over 414.029 centimeters cubed. And that's going to give us a density of the juice equal to 1.16 grams per centimeters cubed. And then now, final step, we can get the specific gravity. And we know that specific gravity is going to be equal to rho of the juice over rho reference. And we just figured out density of the juice is 1.16 grams per centimeters cubed. And the density of water is 1 gram per centimeter cubed. Therefore, our specific gravity is 1.16. And that is unitless because these have the same units. So, I lied when I said last step. So we actually have one more step. We are supposed to state any assumptions that we make within solving this problem. So the assumptions that we make, because assumptions are really important to document. Our assumptions are our first assumption would be that we were able to squeeze all of the juice out of the oranges and that there is no juice left in that pulp and orange peels, really within the pulp. So we got all of the juice out, and 1.75 cups is the maximum amount of juice that was going to come out of those 6 oranges. So the first assumption is we captured and squeezed all the juice. And you can see how that assumption is important, because say we still had some juice left in the pulp, then that would give us a different mass of the juice, because we wouldn't really be able to account for whatever juice is in that pulp. It would throw a mass balance off. That would therefore throw our density off and our specific gravity, and it just trickles down. But since we assumed this, it made this problem easier. And then our second assumption would actually be that we were able to accurately measure all of these weights and volumes. So it would be that we have accurate measuring devices with no uncertainty.